I don't understand how to make this stop.
You can turn that off.
Okay. Look, guys, I wasted some time I should have spent doing something more productive. I used to just have a black rectangle on the right-hand side. I actually took the texture from behind and copied it over there.
What?
Can't you tell? It's all pebbly instead of just being flat gray. Okay, so I had a question. Are there people who didn't get to eat with me who really want to go out to eat with me still? Yes. Well, if I went to eat on Friday at, say, for example, College 9, would that fulfill the need? Okay, then I'll do that. What? Probably not. Yes. Who don't have what? It costs $8. Is that cheaper? I mean, people come and just sit there sometimes. It's guaranteed what? I like the food there. Okay, let me say again, you want to come to the final. I will be unpleasant about it otherwise. Hey, did you guys see you have a whole mess of graded quizzes and homeworks up in the grade plan?
What?
I didn't do it. It wasn't me. We have MSI tutors, none of whom have come to class today. Permutations and combinations. Okay. Escúchanme. Cállate. Escúchanme. Permutations, order. Combinations, order does not count. Permutations, so for example, if you just want to know, suppose I'm going to pick 3 people at random from this room and give them $5. Hi, Darren, I'm teaching now. Tell me, will I be able to flush the toilet tonight? Really? I think my guess is that entire problem with all the water was probably the toilet in Jason's room was running. And that's what no? Okay, bye. So, I didn't have a toilet this weekend. It was terrible. What? No, that was my employee.
Does he listen to these recordings?
I hope not. It would bore the shit out of him. Okay, what's the nicest way I can say this? Okay. My contractor, my house is flooded. The flooring in my house looks like this. I mean like this tall. It's horrible. You brought me something. And some money. Oh boy, lucky me. And cookies, thank you. Okay. Did you get something for yourself too? Thank you. Okay, permutations, order matter. So, if I were to pick 3 people at random from the front row and give them cookies, they wouldn't care what order I gave them cookies to. They would only care that they got cookies. Right? But if I picked 3 people and the first person got a full cookie and the second person got a half a cookie and the third person got a quarter cookie, they would care about the order. Okay, so permutations, order matters. There's a ton of things where people try to get answers about probability or counting, and they don't get the right answer And the difference is the whether or not order matters, an assumption about whether or not order matters. It's very common to overcount because you've come up with an answer where order matters, and in fact, order does not matter. I'm going to eat cookies during lecture. Let's put it this way. Would you rather I be bitchy and not eat cookies, or eat cookies and be less bitchy? Still bitchy, but less bitchy? Okay, let's try this. Fuck you, Alex.
Everyone in lecture can hear that.
I think the whole point, I bet there's someone else named Alex here. Raise your hand if your name's Alex. That he's the only one? That ain't right. I forgot to eat lunch. I'm starving. Actually, I was working tirelessly to try to get more class seats in computer science and electrical engineering classes, to tell you the truth. Okay. So, that whole thing, you guys have a tendency to be kind of freaked out by factorials. Factorials are not freaky. All that is, if you have a set of size, everyone in this room, let's just guess. Say there's 150 people here. Since there's 400 people in the class, I think 150 is conservative. So, if I were to pick 3 people at random out of this room, there would be 150 choices for the first, 149 for the second, and 148 for the third. And the way you would write that is you would write down 150 factorial over 146 factorial. And that just means 150 times 149 times, make that a 7, times 148. You see, because all the others basically cancel out. Does that make sense? Don't get freaked out by terminology and notation. When you start a new thing that you know about, there's vocabulary, notation, terminology, and then once you get it, it stops being intimidating. So I'm encouraging you to move to where you stop being intimidating. This is the answer for if I pick 3 people in order out of here. Maybe I'm going to give them cookies. But if I'm just going to give all 3 people the same cookie, it doesn't matter what order I give them to, which means I'm overcounting by the number of ways you can put 3 people in order. Suppose it was Michael, Kevin, Brianna? No. Help me. Sorry, Lindsay. Lindsay and Kevin. And what? Misha. I would never have remembered that. Okay. Misha and Kevin, and I've already forgotten. That's how good I am. Lindsay. I'm so sorry, Lindsay. Okay. So if I'm going to give all 3 of these cookies, it's not different for me to give them the cookies bing, bing, bing than for me to give them cookies bing, bing, bing. And the number of orders I can get is her first, her second, him last, her first, him second, her last, her first, her second, him last, her first, him second, her last, him first, her second, her last, him first, her second, her last. And that is 3 times 2 times 1. 3 choices for the first person in the order. Then there's 2 left over for the second person, and then you have no choice at all for the last. In fact, when you're doing these counting exercises, if you're at all intimidated or upset, think to yourself, what is constrained? There's a certain kind of problems they ask in the book that freak people out that aren't that bad. For example, suppose we ask about bit strings, and we say, how many bit strings are there that start with 3 1s or 3 0s, right? Well, 3 1s start and end with 3 1s or 3 0s. So let's just count the ones that start with 3 1s. You've constrained everything but the 2 guys in the center. How many different guys can you put in the center? 4, because that's 2 choices for the first and 2 choices for the second. So there's 4 strings with 1s like that. And there's 4 strings with 0s like that, so there's a total of 8 strings. If you think about what's constrained and what's free and how many degrees of freedom you have, the answer often becomes easier. Okay. I'm happier with cookie. Okay, but, so I have to divide this choice by 6 if order doesn't matter, because I've overcounted by 6 when I use the ordered answer as the unordered answer. Does this make sense? Okay, so combinations. You take the ordered answer, actually let me go to a color. You take the ordered answer and then divide by the number of times you overcounted for the ordered answer. That's all combinations are. I'm always going to read that, n choose k. If you want to read it C of n comma k, that's your business, but I think it's less informative than n choose k. Another way to say it is the number of subsets of size k taken from a source set of size n. Does that make sense? Okay. So, cards. We'll have lots of questions about cards. Let's talk about cards. Okay. So, do you ever have trouble remembering the order of poker hands? Which ones win? You don't know of them? You don't have to know any of them, because all you have to do is count them. If I ask you about poker hands, I will tell you exactly what I mean. For example, I would say, how many flushes are there taken from a deck of 52 cards? Does everybody understand what the 52 cards are? Yes. When you are, I'll tell you in just a second. I'll tell you exactly what I put on the quiz. If you're trying to see if you've counted the number of poker hands correctly, make sure you've accounted for the suit and welcome, my sole attending MSI tutor. You get a cookie for coming to class. So, on a quiz, I would say, how many flushes are there from a deck of 52 cards? A flush is 5 cards of the same suit, no matter what rank. A flush is 5 cards from the same suit, 5 same suit. So, for example, the Queen of Hearts, the 10 of Hearts, the 4 of Hearts, the 3 of Hearts, and the 2 of Hearts is a perfectly good flush. If you're playing poker with someone, you'd probably call this a queen high flush. Okay? People who are first learning about poker are often confused why flushes are more valuable than straights. A straight is 5 cards in consecutive order. Doesn't matter what the suits are of any of the cards. So, for example, a straight would be like Queen of Diamonds, Jack of Clubs, 10 of Hearts, 9 of Hearts, 8 of Diamonds. That's a perfectly good straight. Look across that T. Isn't that exciting? Okay? It looks kind of like my signature, which kind of goes. Okay. So, be brave. Tell me, how many of you think it's weird that a flush is worth more than a straight when you play poker? Okay, we sort of talked about this just a little bit. So let's talk about how many flushes there are. Well, first of all, I'm going to multiply 4 times the answer I get for the number of heart flushes there are, right? Because the number of heart flushes is the same as the number of diamond, is the same as the number of spades, is the same as the number of clubs. That's fun. Let's just do this for the rest of the class. Okay, so out of the 13 heart cards, pick 5. We're done. That's the whole answer. Times 4 because There are 13 choose 5 heart flushes, but I asked for how many flushes there are. So I want hearts plus diamonds plus clubs plus spades, which is 4 different kinds of the same answer, which is 4 times 13 choose 5. Okay, which is not an incredibly huge number. Okay, so how many straights are there? I'm going to switch colors. There are the straights, the ranks are uniquely defined if you either give me the lowest card or the highest card, right? If you give me 10, it has to be, and you say that's the lowest card, it has to be 10, jack, queen, king, ace. There's no other choice. If you give me ace, it has to be ace, 2, 3, 4, 5. There's 10 possible low cards, because there's ace, 2, 3, 4, 5, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, and so on until you get to 10, which ends in ace. So there are 10 different straights. No, suits don't count in straights. There are 10 different straights rank-wise. Now, once you've chosen your straight, you have to get the suits of each card. And each card is independent which of the 4 suits you get. So it's 10 times 4 to the 5th. Because it's 10 times 4 times 4 times 4 times 4 times 4. I pick up the first card. I know it's a 10, but is it a heart, spade, club, diamond? I don't know. It doesn't matter. It's a straight. I pick up the next card. Is it a heart, club, straight, or spade, or diamond? I don't care. But they're different hands. They're completely different hands. So it turns out, if you multiply this out, this is 4 times 13 times 12 times 11 times 10 times 9 divided by 5 times 4 times 3 times 2. Let's take 4 and 3 and cross out 12, and 5 and 2 and cross out 10. So now we have the answer is 4 times 13 times 11 times 9. I'm not even going to try to multiply that. I would not get the right answer. So this is 4 to the 5th is a big number. Say, let's just make that 4 squared, so it's 10 times 16 times 16 times 4. Just to sort of vaguely bring it up to that, it turns out this number is smaller than that. Do you believe that? Yeah. Okay, and because the top number is smaller, that is why flushes are more valuable. You never have to memorize hand order. All you have to do is calculate it. So let's do another one. Okay, good, because while you talk, I'm going to eat a cookie. I know what straights are. They have to be in order. If you give me an example of a straight. That's a 2 low straight or a 6 high straight. You can refer it to either way. It's just a convention. A 6 high straight always has the same 5 cards in it. 2, 3, 4, 5, 6. So 6 is the lowest high card you can have in a straight. Well, actually, that's not true. A 5 is the lowest high card you can have a straight, because you can have ace, 2, 3, 4, 5. So your high cards can be 5, 6, 7, 8, 9, 10, jack, queen, king, ace. There's 10 of them. I find it quicker to think of the low cards because the low cards are ace through 10, which is like 1 through 10, which is, I've been counting to 10 for like a long fucking time. I have. I was exceedingly proud of how high I could count at some point until I figured out that you could always count one higher. Yes? Okay, so you see why flushes are more valuable. Okay, let's do a full house. Full house is 3 of one kind plus 2 of another. So like queen, 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 ace, ace. Okay? What?
Just in case two reference, in case two have flaws, what's the tiebreaker for that one? There's kind of there.
What do you mean?
So if you and I are playing poker, you get that. Let's say I get like.
Do you know how card games work? If I have 3 queens, you can't have 3 queens because there's 4 queens.
If I get 3, saying if both of us have a full house, who wins?
The high card, the trips.
For the trips, okay, that's what I was wondering. I didn't know it was the trips.
That's just convention. They could do it any other way they wanted. Okay, so for the 3 of a kind, there's 13 choices. I don't understand what's doing. 13 choices for the trips, 12 choices for the pair. The trips, out of the 4 suits, you have to pick 3. Out the pair, out of the 4 suits, you have to pick 2, and then you're done. So this is 13 times 12 times 4 times 6. Why is this doing this? I've killed all the apps. Why is this doing this? No, it's not a ringtone. It's not an alarm. All my alarms sing obnoxious music at me so I get out of bed.
I thought that thing was fixed. I thought that was the particular problem.
How many is 13 times 12 times 4 times 6?
3,744.
Okay, so 3 blah, 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 blah. Right? So 3 blah, 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 blah is less than 5 blah, 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 right? Which is less than 10 blah, 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 blah. Yes? Okay. For each card, make sure you choose the rank and the suit. I go for ranks first, always. How many different ranks do you have a choice for your 3 of a kind? 13. How many do you have for your 2 of a kind? Okay, now that you've picked the ranks, let's pick the suits. Out of 4 cards, how many different suits do you have to pick for 3 of a kind? Oh, I love that sound. Forgive me for eating, I'm sorry. You know what's crazy? I actually brought lunch today. It's in my office, not helping me in the slightest. Okay, are you good, Jackie? Okay, so what about how many straight flushes are there? Well, first of all, there's 4, because the same answer that you get for diamonds is the same answer you get for hearts and clubs and spades. And there's 10 of them, so there's only 40 straight flushes, period. So that's why straight flushes are so valuable. How about 4 of a kind? There's 13 choices for the rank of your quads, your 4 of a kind. And now you have to, and you use all the suits, so you don't have to think about the suits. Now you have 12 other choices for the rank to fill it with, right? You have 12 other choices for the, because 4 of a kind is something like ace, 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 queen. So, but it could be ace, 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 ace 2, or ace, 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 ace 7, or ace, 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 jack, right? So there's 12 choices for the rank of the last card. We call it the whole card. And then you have to pick the suit. And there's 4 choices for the suit. So you can see that's more than 40. And that's why 4 of a kind is less valuable than a straight flush. Straight flush, more valuable than full house. Full house, more valuable than flush. Flush, more valuable than straight. Straight, more valuable than 3 of a kind. 3 of a kind, more valuable than 2 pair. All of this is not memorization, it's figure out how many of them there are. The more rare it is, the more valuable it is, which is how De Beers made a bunch of money selling a load of malarkey to Americans about how much diamonds they needed to prove they love someone. Should be 2 months' salary.
Something's telling me the story behind that.
Just outrage. Okay, makes sense? I love to ask combinatoric problems. Okay, we haven't talked about probability yet, and I've been asked by the W people to not spend very much time talking about probability because basically all of you are going to take probability independently. You're all either going to take CE 107 or AMS 131. So, AMS 131? You don't know that you have to. Trust me, you have to. It's in the next year's catalog copy. Okay. Actually, you don't have to because you took CE 16. This makes me want to throw my phone on the ground. What?
I swear, I thought you gave that to somebody and that person fixed it.
They told me it was some sort of like My Noise app, but I've killed all the apps. So I don't understand why it's making noise. Okay. But then you'll have to unlock it again unless you touch it every once in a while. Touch it, touch it. Okay. Have you seen that video about I'm going to touch this fishy? I'm going to touch the fishy. Touch the fishy. Next time I will show, on Wednesday, those who show up early will get to watch the I'm going to touch this fishy video. It's not X-rated or anything. Okay. The only thing you have to memorize is what a deck of cards looks like. Understand that each card has a rank, each card has a suit. That's all you have to memorize. Okay? Let's go on talking. Let me see. I want to talk to you about Pascal's identity. Okay, let us prove that n choose k plus n choose k minus 1 is equal to n plus 1 choose k. Okay, first I want to tell you that this is reasonable by giving you a combinatoric argument. Okay, suppose we have a set of n things, and then we add one more. But see, all of the n things are green dots. And we're going to add one more, and it's a special red dot. Okay? And now I want to make sets of size k, k-sized sets. Now, there's two things I can do. I can take k things out of the n I had before, or I can take k minus 1 things out of the n I had before and include Mr. Red Dude. A lot of math arguments go like this. We've created a distinguished member. We're saying that's the last dude who was added. Now, if you already know how to make k-size subsets out of n, do that. And they're still legitimate for k-size subsets out of n plus 1. But it didn't count all of them because it didn't count any of the sets that included Mr. Red Dude. Mr. Red Dude, once you put him in your k-size set, now you only have room to put k minus 1 other ones in there. Make sense? That's called a combinatoric argument. I want to show you an algebraic argument. Okay? So, n choose k, known as n factorial over k factorial n minus k factorial plus n factorial over k minus 1 factorial n minus k plus 1, k minus 1 factorial, okay? 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 Okay, first I'm going to rewrite this, and this one, just the one on the right, I'm going to rewrite it as n, actually I'll just do it right on the same line. Instead of n minus k plus 1, I'm going to distribute them negative 1 through the k minus 1 and write it in slightly different order, so that now it is n plus 1 minus k factorial. That's just a little tiny bit of algebra. That's all I did. Okay, but now you can see the guy on the left has one more k in his factorial. here's an important thing to note. 7 factorial times 8 is equal to 8 factorial. And in fact, k minus 1 factorial times k is equal to k factorial, right? Okay, so look at the guy on the left. There's a k in the denominator that does not appear on the guy on the right. On the other hand, there's an n plus 1 minus k in the denominator on the right that does not appear in the guy on the left. So remember grade school or high school or whatever? We're going to multiply the guy on the left by n plus 1 minus k, top and bottom. And we're going to multiply the guy on the right by k, top and bottom. Watch this. I'm seeing some for tumult things. This side we're going to put n plus 1 minus k over n plus 1 minus k. This side we're going to put k. All we're doing, remember back when you were asked to add 1/3 plus 1/4, what did you do? 1/3 you multiplied by 4 over 4. 1/4 you multiplied by 3 over 3. Now you have 3/12 plus 4/12 to get 7/12. That's all we're doing. We're normalizing denominators. Okay? So that means if I do just a little tiny bit of math, I have n factorial times n plus 1 minus k plus k over k factorial n plus 1 minus k factorial. And the k's cancel out. So I am left with n factorial times n plus 1 over k factorial n plus 1 minus k factorial. And this guy here, n factorial times n plus 1 factorial is just n plus 1, the quantity factorial. And guess what that is? That. Make sense? I'm not sure it'll be this one, but I will give you some problem that is relatively straightforward algebraic manipulation about binomial coefficients on the next quiz. It could be another one that involves normalizing denominators and shit. Okay? My pants are falling off. Okay, so the big deal when you're thinking about answers for this is, does order matter? Let's talk about binomials. If there's a problem on your quiz and it asks, what is the coefficient of x to the 13, y to the 12 in x plus y to the 25? First of all, if someone asks you this and this number plus that number doesn't add up to that number, they're smoking crack. Okay? Okay? But the binomial formula says that the coefficient here is 25 choose 13, or if you like, you can use 25 choose 12, because as you know by now, 25 choose n is the same as 25 choose 25 minus n, right? 25 n choose k is the same as n choose n minus k. Yes. Okay, and it's okay if I call n 25 because he and I are, known each other for a long time.
Oh, I see what you did.
Yes. Say that again.
You're not going to mix this up and put an exponent quantity? Like x squared plus y instead of just x plus y?
Oh, you should be able to handle that.
Yeah, that's easy. But then it wouldn't add up.
It's just a variable change.
Yeah.
You could do, I could do.
So then it wouldn't add up to 25 then.
Have mercy on us.
It wouldn't. This is what I would do. I would say, hey, in this case, x is equal to z squared. Come up with the whole answer, and then change x into squared, and then it would be x to the 15th. Make sense? Because I'm a computer scientist, and I like to call helper subroutines. Yeah. Okay. The binomial theorem, suckers. We're going to learn to prove the binomial theorem by induction now. Okay? So, let me tell you, while we do this proof, there are a few things that techniques we're going to use. You've seen them all. One is that the summation from I equals 0 to n of something, we can take the 0th element and write it all by itself and then add it to that same summation from 1 to n, right? You can pull off the first dude in the sum and write him by himself if you want. Also, you can pull off the last dude and write him by himself. Also, if you get tired of that later, you can shove him back in. We are going to watch it happen. I see you looking confused, but I'm going to make you happy, personally. You, with the wavy hair and the green sweater. Yeah.
What about my excitement?
I'm losing it. Let's do it. Okay. Let's go down here. So, I'm just going to do the inductive step. The basis step, it's not trivial. You need to do it. But it's not interesting, and we're going to spend a lot of time on this. Okay, so would you like me to assume that the binomial theorem holds for n and prove n plus 1, or holds for n minus 1 and proves for n? You tend to like the former, but I prepared the latter. Okay, so let's try to use the brain-dead theorem. So I'm going to assume, I don't want to do that right now. Later, maybe. We're going to assume, see how I'm assuming that x plus y to the n minus 1 is equal to that? That's our inductive hypothesis, also known as our IH. Okay, so x plus y to the n is equal to x plus y times x plus y to the n minus 1. Brain-dead theorem. Brain-dead theorem says here is the left-hand side of p of n, and here is the left-hand side of p of n minus 1. So I am going to replace the left-hand side of p of n minus 1 with the right-hand side of p of n minus 1, and then multiply through. So that is x plus y times the summation from I equals 0 to n minus 1 of n minus 1, choose k, x to the n minus 1 minus k, y to the k. Okay? Now I'm going to multiply through that x and y, leaving two sums, one of which has an extra x and one of which has an extra y. It's almost like a monkey could do this, right? All I'm doing is just doing the only obvious thing to do. It's kind of like I sat here and said, man, I don't know how to do this at all. How about if I just try the brain-dead recipe and then just multiply stuff? There was an arm in this region. Yes? Yeah, K's a better letter. We've always wanted K's. This is going to leap onto the ground, I can tell. There we go. Okay? Sorry. Okay, so that means that it is equal to the summation. Actually, I'm going to start writing it right up against the edge, just to give me more room. So we have the summation from k equals 0 to n minus 1. N minus 1, choose k. X to the n minus k. Y to the k. Plus the summation from k equals 0 to n minus 1 of x to the n minus 1 minus k, y to the k plus 1. Now, y to the... k plus 1. What's wrong? That's just a very sloppy person who probably shouldn't be allowed to teach people. Okay. What's our goal? Our goal is to somehow manipulate these two things and add them back together. Why can't we add them back together? Well, we need to be able to add them up. Look over there. If we did a variable change such that k went a different place, then we could make it look exactly the same. So instead of going, and this part, let's leave this part alone, and let's come up with a variable change. Instead of using k, we'll use j. And now, where, you know how, let me show you something real quick. So, the summation, suppose we're adding up I, and we take from k equals 1 to 3. That's equal to 1 plus 2 plus 3, right? Okay, what if we have the summation from k equals 3 to 6? I'm going to add something up 3 times, but instead of adding up I, actually, I shouldn't change the variable here. I want this to be exactly the same. Oh, look, there was a k there. Okay, I want this to be exactly the same sum. So instead of just putting j here, I have to put j minus 2. Right? When j is 3, I add up 1. When j is 4, I add up 2. When j is, oh, it's not 3 to 6, it's 3 to 5. Sorry, excuse me. You have to be careful with off by 1 errors in these things, guys. So 1, 2, 3, 1, 2, 3. 3, 4, 5, 3, 4, 5. When I had 3, 4, 6, I was adding 3, 4, 5, 6, I was adding up 4 things. So this is a variable change. I'm going to do that in our binomial proof. Okay? So if I go back to our binomial proof, I am going to change this dude here. Let's put him over here just so I can, I'm just going to play with this guy. This guy right here is going to become the summation from j equals 1 to n. Instead of going from 0 to n minus 1, we're going to go from 1 to n. What that means is that everywhere there used to be a k, I have to make it so it'll be the exact same sum. So when k was 0, we added up n minus 1 first. So we need to put x to the what? Ooh, I've lost the binomial coefficient.
Yeah, I was going to ask about that.
We need to have n minus 1 choose k. Okay, so we need to have here, when k equals 0, the first thing is n minus 1 choose k. So when j equals 1, we need to have n minus 1 choose k minus 1, right? Because we want the same sum with just a change of index. That's all we want. Yes. I don't know what my problem is. Okay, so when k is 0, we want this to be x to the n minus 1. So we have, what is our new thing we're going to put there?
J, n minus 1, J minus 1?
We can see x to the n minus k. Because when j is 1, it'll be the same, x will have the same exponent as when k was 0 and the one above. See?
Yeah, but we don't have k in the summation.
Ugh. Okay? Make sense? All I'm doing is a change of index. Everywhere you used to have a k, you now have a j plus 1.
So it shouldn't be n minus j plus 1. Oh, no, never mind.
Okay? And y becomes just k. Oh, j! Okay? Now, the exponents that I use different letters. But that guy on the right is exactly this guy, the green guy that is for the right, it's got exactly the same exponents as the guy on the left. But this one starts at 0 and goes to n minus 1. Whoops, sorry, this one starts at 1 and goes to n. And this one starts at 0 and goes to n minus 1, so they're like this. So you know what I'm going to do now? Just a second, Joe. I'm going to write the bottom one of the one that starts first by itself, and I'm going to write the top one of the guy that ends last by itself, and then I'm going to add together the ones that line up. Yes. Okay, so I'm sorry, I'm going to have to switch pages. Okay, the point that we're at right now is we have the summation from k equals 0 to n minus 1 of n minus 1 choose k, x to the n minus 1 minus k, y to the k, plus the summation, and I'm going to go from j back to k, just so they're the same variable. It makes it obvious that we're adding them up. From k equals 1 to n of n minus 1 choose k minus 1, x to the... Is it an emergency? I'm lecturing. Bye. Where am I? Sorry, I just need to make sure that I get this right. N minus 1 choose k minus 1. Yes, yes. N minus 1 choose k minus 1, right? N minus 1 choose k minus 1, x to the n minus 1 minus k, y to the k. Yes, into the, what?
It should be x to the n minus k.
Oh, it's n minus k for both of them. That's why. Okay. It's hard not having a duplicate page here. So n minus k, it's supposed to be n minus k for both of them. This will look much better when it's all recorded and I don't have trouble going back and forth between them. Okay, so it's important that they have the same exponents. The problem is that one of them goes from 0 to n minus 1 and the other one goes from 1 to n. So we're going to write the top guy by himself and the bottom guy by himself. Okay, so the sum on the left, let's write out what that sum is when k is 0. When k is 0, what you get is x to the n. Right? Just plug 0 in for k and see what you get there. Okay, so I have x to the n plus the summation from k equals 1 to n minus 1. N minus 1, choose k, x to the n minus k, y to the k, plus, now I'm going to write the nth term for that guy all by himself. So it's the summation from k equals 1 to n minus 1. N minus 1, choose k minus 1. X to the n minus k, y to the k, plus y to the n. The y to the n is the term you get when, sorry, it's not, it doesn't, when the index of k is n. So this guy here, actually let me change the color here. This guy is the last term in the sequence that ends higher, and this guy is the first term in the sequence that ends lower. If you're feeling awash in notation and a little bit confused, I promise you, it will all make more sense once you get it fully internalized. It really isn't that bad. I'm not trying to give you crap if you don't get it yet, because like everything else in computer science, it's disturbing and like lights are flashing in front of your eyes until you get it, and then you get it and it's like, it's not a big deal. This is not a big deal. We can do this. Okay? So, but the thing is, look at the guys inside the black box. Same exponents, same range. You know you have blah plus blah plus blah plus blah on one side and blah plus blah plus blah plus blah on the other. We can combine these all into the same sum. Okay? So that is the summation from k equals 1 to n minus 1 of n minus 1 choose k plus n minus 1 choose k minus 1 times x to the n minus k, y to the k. And remember, we still have x to the n plus y to the n, like that. We just proved Pascal's identity, and that's what's in those square brackets. Okay? So this is equal to x to the n plus the summation from k equals 1 to n minus 1 of n choose k, x to the n minus k, y to the k, plus y to the n. Okay, look at this sum that starts at 1 and ends at n minus 1. If it were to have a 0th term, what would it be? X to the n. I'm wiggling my eyebrows. You can't see it in the back, but I am. I'm waggling suggestively, because this is like math smut. Okay. See that term right there? If it were to have an nth term, what would it be? Y to the n. So we did this proof by having two separate sums, changing the index on one so the exponents would match, then writing the first guy of one all by itself and the last guy of the other all by itself so you could add them together. Then we added them together, and now we're going to shove the leftover guys back in. Okay?
When you brought up the y to the n, is that the n minus 1th term? Or no,
that's the nth term, because that sum went from 1 to n as opposed to from 0 to n minus 1. Okay? And the whole thing is now equal to the summation from k equals 0 to n choose k, x to the n minus k, y to the k. And we're all done. Stop that. Yeah. Take a picture. Take a picture. Oh, come on. She's the only one that wants a picture? Are you done? You wrote it all out. You fine individual. And now we're done. Okay, this is just the inductive step. You need a basis step. Let's go back and talk about what the basis step should be. The basis step should be, oh look, I wasn't using the fast shortcut. The basis step should be what happens when n is 0. Well, x plus y to the 0, guess what that is? 1. The sum from 0 to 0 of anything choose 0, I mean, basically you just have x to the 0, y to the 0 times 1. So it's all 1. Right? The basis step is not hard. All you have to do is set n to 0. Okay, so this is a good inductive proof because the basis step is totally doable because x plus y to the 0 is boring. And so is that sum when the index stops at 0. It's boring. Both boringly 1. And then for the inductive step, we assumed that the thing we're trying to prove holds for n minus 1. And we use that assumption to prove it for n. Right? So that, my dear friends, ladies and germs, is the binomial theorem. Okay, using the binomial theorem, that's where your homework comes from. So what is the coefficient of x to the 12th, y to the 12th, and the expansion of 2x minus 3y to the 25th? You need to know how to answer this. I get another like 9 minutes. You're all fussing around like I don't get to talk for 9 more minutes. Okay. So basically, you write out what it's equal to by the binomial theorem, and then you set j equal to 13 and figure out what the coefficient is, which is 25 choose 13 times 2 to the 12th times negative 3 to the 13th. Does that make sense? Probably going to be something like that on the quiz, guys. Well, I often give you like 5 topics, and I never ask more than 3 questions. When I have too many things to put on the quiz, then I just save the problem for the final. Okay, so this is cool, guys. Coolness alert. Coolness alert. So instead of looking at x plus y to the n, let's look at 1 plus 1 to the n. That is to say, 2 to the n. So 2 to the n gives you all subsets of all sizes. That's what that says up there. This is another way of looking at power sets. This is what, as a mathematician or an engineer who likes getting right answers, loves. A different way of looking at the same problem where you'd use a different mathematical technique and you get the same answer. That shows that your world is consistent. And it makes the probability that you made a stupid mistake on your quiz go way down. Okay? If I piss him off, he's going to beat me to death with a stick, I think.
Oh, screw the guy who actually happened to be a kendo,
Yes. Somebody told me you're a kendo sensei.
No, it's a secondary class. Oh. Just. Right, Rob.
I'm not a multi-billionaire, I'm just a billionaire. I'm not a billionaire at all, by the way. I live in a house with no toilet and completely warped floors. My house is having problems with the recent rains. And you know what it is when you own a house? You don't get to call the landlord to fix the shit that goes wrong. You get to pee in the garden. I don't have any plants.
No grass? Okay, your neighbors.
No grass. No, I have a lot of succulents. Succulents are like a form of cactus. Okay, a lot of things we like to do with binomial coefficients involve inequalities. So, let me warn you guys. There aren't very many things in this class I ask you to memorize. Almost none. I tell you how you can rederive almost everything. You can rederive the binomial theorem if you just sit around and multiply x plus y times x plus y and then take that result and multiply x plus y and then take that result and multiply by x plus y. I think it would be beneficial to you to actually memorize the binomial theorem. So you want to memorize this thing. X plus y to the n equals that summation. You probably want to memorize that. Or, why would you memorize Pascal's triangle? You can rederive it anytime you want. It's just that a lot of the things I'm likely to ask you on the next quiz come from the binomial theorem. Like, what is the coefficient of x to the 13, y to the 12? You know, that kind of thing. Oh, you can come in if you want. The architecture people are restless. Pascal's triangle, we proved Pascal's identity with a combinatoric argument and a non-combinatoric argument, right? I'm not sure what I should talk about on Wednesday.
Can you go over like the way of thinking about combinatoric arguments? Because whenever the homework threw one at me, I was just like, I have no idea.
Okay, a combinatoric argument means something like I said about Pascal's identity. Hey, if you're going to take k-size subsets out of n, and you already have an answer for k minus 1 size subsets out of n minus 1, you can use that to build your new thing. It means a reasonable argument having to do with stuff you know.
I just don't feel like I know a lot of this stuff. I don't know. It feels like there's a set
Should
of
we engrave that and put it over your bed? I just don't feel like I know a lot of stuff.
I told you I'm done.
Put it in his, put it like.
I feel the restlessness increasing exponentially.
Photo of him and just like.
Hey, could you tell me which part of what I talked about today is most upsetting and you want me to review on Wednesday, please? The binomial theorem proof? I will do the binomial theorem proof again on Wednesday.